So just to give a recap of what we like, this is a continuation from last day's meeting. Uh, so basically, PyTorch guys came up with some framework known as PyTorch compile. So why do you need PyTorch compile altogether? Because like itself has overheads and all, and the main point is you can get the computation graph out of your Python program, and then you get a no Python thing. Like you just chop off Python totally, and then you work with the IR and all, and you can do some certain optimizations like operator fusion and all, and then you can just get benefit out of it. So the last time where I stopped was like just the container of the various IRs which they use, that is FX graph. Okay, so like now let's
So why did they give this name FX?
function x something like that, fx something, f of x graph, something, some kind might be something like that, something like that. So basically, so this fx graph is a data structure, and internally the fx graph has nodes. So each of the node has some opcode. So like this on the screen which are shown, like I have already discussed last time, but still just to give a recap. So placeholder is what is the input to that particular graph. uh, Get attribute is like you get the attribute of that particular module. Call function, you call some function. Call module is you call some module, and output is just the return statement of what you.
The entire graph, you will have multiple nodes.
Yes,
And what is the node data structure here?
the node data structure is like there is an fx graph. So like as
This
in
is node or graph?
this is whatever is like this is node. So like as in if you see, so there can be, this is like fx graph. Inside it, if you see, there shall be various nodes like this. Okay, so this might be placeholder, this is the input, and then there is some operation, like there is some function call and all, and then ultimately this is some return.
Fusion happens before it gets this thing or after?
The after, like you this is just a container of what is there. Like you can just do something out of it, and like you work on the graph, and then basically after that you get some
Fusion, in case of the dot inductor, which does the fusion operation on the before it?
no, at the end, torch inductor.
Inductor is
Yes. So I shall be going into each of them like briefly. So just to give an idea, ki like how last day I show you, told you, right? Like they get the fx graph out of the PyTorch program. Okay, and then that is some kind of a control flow analysis. Then they need to do some kind of a data flow analysis, which they use called symbolic execution and all, and so that you get the type information of each of the stuffs. So they like this is something.
So, but the graph itself.
Mm-hmm.
I'm not talking about the type. The graph structure, is it control flow only or determined from the control flow only, or?
I guess the way they design the graph, so there it is based on control flow itself, like as in one graph, like internal mechanism of the graph is based on how you are doing the operations and all, like the internal nodes of a graph. Okay, there is a graph.
True.
Okay, now how,
Control flow or the data flow? There is no other flow, right?
like like this is a bit complicated here. Inside a graph there shall be many nodes, and that node shall be joined together based on the semantics of how, what are the operations inside that enclosing graph. Okay, now
Semantics.
yeah, semantics. Now if you are having some kind of a PyTorch program and you run TorchDynamo on it, okay, so there shall be control flow and there shall be graph breaks. Each of the graph breaks shall be constituting your like fx graph, and those fx graphs shall be stitched together based on your control flow analysis.
So FX graph, you are stitching together the control flow, that makes sense. Within the FX graph, the nodes are the semantic part I don't understand.
Like as in if you are having just to we have that graph here. Give me a minute. So suppose if we are having a very basic example, okay, so your fx is just sine square x plus cos square x, okay, something like that. Now if you try to create an fx graph out of this, so the graph would look something like this. As in, like it is based on how the semantics of that sine square x plus cos square x is. Like you get some x. If I zoom it, then it shall cut off from the screen. Entire graph shall not be visible. Okay. So like the x is the input, and the opcode is placeholder, and then you do call function.
Which is because of the input.
Yes.
In input, opcode is placeholder, right?
Yes. X is the input because like
now users is like the out degree.
Yes, number of users.
Which is the out degree.
Like there can be like one edge is there. Like you can just trace like who are the users. So like this is x is a placeholder, and then you do it sine x, like the names are like percentage and all fancy, but you get sine cos, then you raise like power, like this is another function call, and arc is power.
And this target that costs us this is understand, like we actually directly call the this thing
like
the
Triton? No, Triton call happens later on. There shall be further lowerings down the line. I shall show exactly how it happens. So this is just a high level overview of just one-to-one mapping of the Python PyTorch program to just some kind of a graph level representation. Okay.
But this is a data flow analysis.
No, this is not data flow analysis. This is nothing.
Like, no, I mean, this is basically just tracking data flow.
Kind of like they do symbolic analysis, symbolic trace of the Python program, and they generate this graph.
But ultimately, this looks more like a data flow, no?
Looks like it, but yeah.
They name it as symbolic execution, like symbolic trace. So like using this, they.
Basically, data flow is the reason why we are calling it data flow. Just let's look at the node output. Trace back, you know, where the source of the operator's input is coming from and the output is coming from. Right? That is in some sense data flow.
So because the data flow is like you're tying together based on say your function, who consumes it becomes the
consumer produces something like that. Yeah. Okay. Yeah, but they don't use the name.
And you mentioned that this way. The way they figured out this data flow and they combine them is through symbolic execution.
Yes.
Yes. But it's absolutely data flow. And this, each of these graphs, you say that it's a control flow that actually links them.
Yes. Like I shall be coming to the point like how they stitch the graphs together. Like every picture shall be clear because this is very complicated in some sense. So just to give an idea, like where we stop, like there is some kind of an interpreter pattern. Like this is just a data flow or something which they are doing, tent analysis kind of. Using which what you can do is like this is just an example. You can just get the shape and data type of each of the nodes involved. Like this is shape as in shape of the tensor, dimensions. Okay, so like some kind of a propagation, data propagation, like information metadata propagation or something like that. So the basic idea is for each node in your like graph.nodes, you traverse it, and based on the opcode whatever it is, you do certain kind of operation. So this is I have expanded it out, but like they name it as interpreter pattern because actually you are traversing to each of the nodes which are available in your fx graph. So they have interpreter class altogether. You can overload each of the methods and do your needful thing. But just to like the point is, we dealt with some function here,
So can you remind this something we have discussed before, like not during this meeting, but another context we have put it. How it is deciding when to actually break a graph? Yes, sir.
Like
multiple conditions, right?
There are like multiple conditions. I shall be showing two of them here.
Okay.
So yeah, it is there. So basically, like there was this function, right? We were just doing add.
Because we also have this opportunity to see when we are breaking fx graph, but we do not need to break the graph. So
like joining two fx graphs.
Two or more fx graph to create one graph. So if you find cases, that's why like fx graph. I think we discussed sometime back, right? Although not discussing right now. That fx graph breaks in conditions. CUDA graph, for this is the way to break. If there is a non-overlapping situation where you are breaking fx graph but not CUDA graph, then those are the opportunities. And
we can just
that becomes an application.
Yes, like we discussed that. So like basically like what example which we were hitting, like which we were continuing, like this is some add operation which just takes in two tensors and adds it. Then we did some kind of a like transformation where we change the add to multiplication. So like just to see like how powerful fx graph is. Then based on that, what you do is like that transformed graph, like transformed graph module, I just passed through this shape propagation thing and just do shape propagate, and just you can see like it gets all the information, like it was like it's a tensor of size 5 and all are float 30. Like this way you can just do data propagation and all. Now comes the problem of symbolic tracing. Like what are the problems of symbolic tracing? So this is one of them. So if you see here, so there is a control flow involved here, like that is dynamic control flow, which they say here. Now based on the value of x, you do the sum, like x is a tensor, you do the sum of all the elements, and if it is greater than 0, then you do torch.ReLU of x or like negate x. Okay. Now if you try to do the symbolic trace using their legacy fx tracer, it comes up with an error, as in symbolic trace cannot be used with control flow. So this is a problem with fx graph. fx graph as is cannot deal with if else conditions. So this is one issue.
Because you know the result, right? Like because symbolic trace.
Yeah, because we do not know the value.
Like, and if the conditional depends on the input value,
we don't know. Like they could have done something like as in, but yeah, we don't know.
I don't think you can't know.
Like as in we can, but we can just branch it, like if then.
Becomes a component. Becomes a component.
What is that?
At any point of time, if it depends on input, then you start giving concrete values.
Exactly.
Yeah.
Then break.
Then it's not a symbolic execution.
Okay.
It's a bit plus.
So like they cannot.
Just make like two different copies.
Oh, yes, I think that's a limitation of FX, but maybe they have done something.
Yeah, that they dealt with it somehow in Dynamo, like Dynamo. Okay, I shall be coming. So basically, like they say, like they can deal with static control flow in some sense. Like this is to just show you. Like just look at here. Like during the constructor phase, like during the constructor initialization, when you are creating the object, you pass in some boolean value which says like whether you need to do this ReLU activation phase or not. Okay. Now based on that, now during the instantiation of the object, this is like without instantiation activation or with activation. So basically you just pass in true or false accordingly. So false here means this portion would not be executed, and true here means that this portion shall be executed. So this kind of if else condition, right, somehow get managed here, as in like if you do symbolic trace without activation, like you just get like you are doing the linear thing and returning the linear value.
So basically, essentially two paths.
Yes, like you are doing like the condition which is there, like during the initialization, as in you have the data,
But essentially creating two having both fall through and the taken from.
Yeah, like these are totally two different instantiations altogether. Like there are two cases, and it is kind of getting hard coded. Okay, that is my point. Like,
It's basically compile time information.
Yeah.
yes, like you are embedding that information, like which if else, but like it is not dependent. Like it is not dynamically dependent any longer. Like static control, for instance, it can deal with. Apart from that, what other cases are there where fx graph fails? Something like this. If you
So
take,
basically, in this case, if you have a instance, you can't actually have a single address graph. You have to have two
yeah,
of them.
so you need to break it, as in like
But
that.
the problem is that this condition, particular one, also would break the Buddha graph, right? You can't have. But these days there is this node, right? What
Yeah.
is the dynamic what?
Conditional nodes.
Conditional node.
Conditional nodes. Conditional with conditional nodes, you can deal with conditions in Buddha graphs.
They are also in the injector. They also had some version of dynamic whatever they call it. No?
Like
That's the
like
dynamic
I like with the dynamic information,
Yes,
like
yes,
the
yes.
dynamic flag. Like I just ran through the workloads,
And the
but did not.
performance was,
The performance was
fine,
worse.
But whatever they tried to do, that is the one that they were trying to take advantage of the conditionals, right?
I don't think like they haven't taken. They have taken use of conditional nodes as such. They have done something else.
That's also an actually there is a lot of things being done.
Yeah, so like
My
that.
only fear is that those torch 2.0 guys will be also doing. They also know what are the. They will be actually this is important. We have to actually make sure that you have to keep a watch on their GitHub and we have to make sure that we are not stepping on their toes because that's not the thing that we want to do. Currently, what we are doing is makes perfectly sense because we are looking at the performance what they have. Pathological cases or integration. Those are fine. I think once you have this, they will be totally happy to, in some form or the other, happy to actually holding your operations to high chance.
Yeah.
Anyway, go ahead.
Right. So like next, if you see here, you are using some kind of like non-torch functions. Okay, torch functions are like those with torch dot something. Okay, torch dot something like torch dot add or something like that. But if you are using some raw functions from math and all, it fails. Like just
that's why also that you will break the graph.
not break the graph. There are ways to deal with it. I am coming to it. As in, like if you just do like this is just some kind of a normalization. The main point in running it is like this program as it like this function as it is runs perfectly. Now if you try to do fx trace, it says ki like length is not supported in symbolic tracing by default. Like you need to do something. You need to do fx torch.fx wrap. So if you do this wrap, then fx graph like legacy tracer shall know ki like I don't know of this function, but I shall be just pasting it as it is. I shall not go into inside it. Okay, so that is what is trying to do. You see here.
But
So
that will be a one node in the graph, or it will be a separate graph by itself. The function that is not part of the torch.
like they shall just do like as in this line here. It is trying to do a length. So this shall be one node. Each line is a node. It shall be a node. Like as in that target.
Even the function that is not part of the torch. If you look at the have there is a node.
Because like it shall be accordingly setting the target there. It shall be taking the function pointer like when you are doing
And
that.
what I'm saying that you would not dig into that function.
Yes, it shall be just as it is. You just place it here. If that function is faulty and all, like when you try to run the code out of that fs graph, it shall fail altogether.
You can't optimize it.
No.
No, so if it has something, then at runtime it will actually go. This is why the guard will come in.
No. Like this is a pathological case where they go back and forth in Python thing. It shall be
Why
just
should it go back and forth? It should just go back once and they should like no, I can't make the deal.
no, like when you are executing, right? So when you are executing, this shall be pointing to some Python function altogether. So this goes out of the pathway of their optimization and all. So
And
if
then what they do?
they actually like if it happens in something like in Triton or something like that, so there shall be provisions, as in like you just walk out of what is happening, do the Python call execution, get the value, and then continue through the optimization. This is a pathological case which they
Okay, so essentially they will do the normal way,
Huh.
get the value,
and
Then
then
continue.
so this is just like some kind of a continuation which they're doing, like keep it aside, I don't know, I shall be just blindly calling it the way you do it. Okay. So this like
Essentially
there,
treat it as a black box.
yes, there can be many things, like as in this is a basic example, but they may just showed it as simple example, like the NumPy and all libraries are there, which Torch has no idea of, but people use them heavily along with PyTorch and all. That might cause this kind of issues. So yeah, so this was
So
the
this will happen only, like of course, it will be happening anytime you are calling functions, not the Python functions.
Triton function is
It's like the Triton wants you on the function, but that will be getting cheated, right? Like, so what I'm saying is that what I'm
Like-
trying to get my head around
Uh-huh.
is that wrap my head around is that you know like under what kind of function call like this will actually happen.
like as in suppose there
Say if you have a two blast, this will actually happen. You call a two blast function.
like basically to give a very naive example which I have seen, it would be something like this. So suppose you are having, okay, I don't know why it is happening like this. So anyways, like suppose there is some like code which you are running, and internally there is some tensor, and you try to create a NumPy array out of that tensor somehow. That NumPy array, whichever like the function call which is there, you don't know how it works. So that shall cause issues in there. You cannot optimize that black box altogether.
Understood.
So-
But what about this functions for the closed source libraries? If you will go.
Like that is the thing, right? That is the reason why you don't know. Like, you shall
Therefore,
be
in
just
that case, you will also give up, right?
yeah, like
There is no option but to give up.
like not give up, as in you shall be using it as a black box.
Yeah,
Call
there
it
is no optimization.
no optimization, like as in like you are running through something, you get a black
Get the
box
data
here,
and
you call it
do
somewhere,
right.
you get the data, and then again continue. Okay, so you can optimize this entire thing, but this shall be considered as a function pointer also, something. And this is they consider as a bad case, because a lot of overhead may come in this path altogether. And in worst cases, they might also do graph break. Graph break, like as in I shall be coming into that portion, like how they are doing graph break. And this was the little primer on what fx graph is. Now let's look into what Dynamo tries to achieve. Like this is the front end of this PyTorch 2.0 framework. So
Not the back end.
front end, Dynamo is the front end.
Sorry, Dynamo. Inductor is the back end.
Inductor is a back end. And so basically what is happening here is like you are having a Python PyTorch program, and you basically want to create a graph representation out of it, just the computation graph. Now the problem with Python program is like you do not have any good way of doing symbolic tracing and all, like sorry, static analysis and all. It is very complicated. We tried doing it, but there are certain tools available, but it does not do the job altogether. Like there are many special cases and all. Now what these TorchDynamo guys, as in PyTorch guys, they like there is something known as PEP50523. Like this is like Python extension proposal. So basically what it did was like it added some hooks using which you can do some fancy stuffs with how Python actually works. So yeah, to bring it in a single screen anyways. So this is the Python program. You get like I am talking about C Python interpreter. Okay, so there are many interpreters interpreters available like Java, Python and all, but let's consider only C Python currently. Now this parser which is there, right, you take in a Python program and you just parse it and get the bytecode. Now this is something which is defined by the semantics of your programming language. This won't change. Okay, this is something defined by Python programming language. Okay, for this program you shall be having this bytecode altogether. How this bytecode is interpreted and executed is defined by this C Python interpreter. Okay, in a basic program how it happens is you get the PyTorch program or Python program, whatever, you pass it through the Python parser and you get the bytecode, and there is this interpreter loop which is running all together, and it shall take each bytecode means just an instruction in bytecode. It shall just run, execute it and give the result, execute it, give the result, something like that. But with that Python extension proposal, what they came up with, like intermediary stage, where instead of just passing the bytecode directly to the C Python interpreter, they came up with some kind of a hook. So before passing the bytecode to C Python interpreter, you can just pass in through this eval frame API. So basically what you can, like, this eval frame API is very powerful. So during runtime you can make changes to this bytecode altogether.
You can write bytecode.
Yes, rewrite bytecode. I shall be coming to this part. Like this is.
Usually in our rebuttal we say that you can, but this is fine.
We were talking about runtime. That is fine.
So yeah, so like you can just rewrite your bytecode during.
In the rebuttal, you just write. You just said that the Sassel can actually write it. Go ahead.
Yeah, so like you can change the bytecode altogether, and what important thing which you can do here is, this is interesting, you can get a compiled object code. Okay, like compiled code object, like if you try to run it, it shall be just some C function or altogether. You just get the compiled object code out of it, and you can just stitch the bytecode in that way. Like you, when this bytecode executes, you just call the compiled code altogether. So this is what they are making use of heavily in their Dynamo thing. Okay, so I'm just, this is too detailed, but let's not go into that.
Eval frame API is provided by Python.
Pythons that after it is there in Python, the C Python interpreter, that is a hook. Okay, now you can just write it on your own, that like this is you overload it and define your logic there and compile it, and you can just do it. Okay, and this came with that Python evaluation enhancement proposal 5.2.3. That's just a name, like it is there in Python. Okay, so there are various flags. You can just to give an idea, like there are various flags using which you can just get detailed information of what is happening when they are just compiling their stuffs. And this is just a library dpyf. So what it does is, basically during the runtime, it can just, like when it is just spitting out your logs, right, you can just get, like, you might not be familiar with what is a bytecode and how it looks like. It just converts it to a Pythonish thing, so that you can just read and understand like what that bytecode actually means. Okay, keeping those aside, let's look at an example. I shall be running Dynamo through it. Okay, so basically what I am doing here is, there is some like toy example. There is some tensor. We are getting the absolute value of it, adding it by 1 and dividing that thing. Okay, like this is just some baby operations altogether. Then it is something similar in flavor to that thing which we saw, right? There is a dynamic control flow. So based on whether this sum is less than 0 or not, you shall be just negating b.
Yes, you can get here.
Yeah. Now, it, basically what I want to show here is like how FX graph breaks happen here and how Dynamo stitch stuffs together. So now, like, this is some internal API which I have used. I have not used that torch compile thing. So basically I am bypassing their inductor backend. Dynamo is there. I am just using my compiler. Like this is a basic compiler which just takes in the torch IR, which is just given out by TorchDynamo, and I am just printing it out. Okay, yeah, semantics is there, like you need to do GM forward and all. Let's not look into it. It is just some kind of a dummy thing.
But the torch IR is very close to the source code itself. Right?
Yes, you shall not get any benefit altogether, just for showing. But they also say here something, like even if you are using this dummy compiler, you get some benefit out of it, because you are caching stuffs and you are getting Python out of the picture.
Okay, so this is more of an, helping on the bug analysis. So this can be enhanced to catch bugs on the Python code, no?
Is it?
This is basically not bug, but
This is, I feel that this is just implemented.
This is
This is what the effective is.
this is not. This is
this
actually
is just looking through the torch
Yeah.
Python code and then
creating a graph out of it, and you can just run that graph. Basically the same thing. Okay, you can just run that torch IR. But
you can run the torch IR.
yes, each IR, like each FX graph. Yes, each FX graph has a code corresponding to it. Okay. Yeah. So like when you can just view the graph, or you can just run the code. Like there is that magic call method using which you can just call. So basically, let's not go into the details of this logs, but let me show you what happens here. So if you look into the toy example here, and this is some, let me reduce the font a bit so that things, is it visible? It is visible, right? Okay. So now if you see, this is the toy example which we looked into. Now this is some compiled function which they are generating. Okay. During the runtime, this is, they are compiling it and just pasting it. I shall be showing it how this is happening, how this stitching of compiled function happens together all together. But for the time being, assume like they have generated some kind of a compiled function 1. So what is happening here? Look into it properly. You like, there is A and B, like they take in that input A and B is there. You just like some local A and B, they do it. They do this operation, they do AB absolute this thing, they add it with 1, and then they generate X, like dividing it. Fine till now. Next what they do is they get the sum, like B dot sum, they do B dot sum. So B dot sum, and then they get the sum out of it. Next what they are doing is they are calculating this less than equal to 0, LT. Okay, less than 0. Now what they are returning here is, they did not do the if else condition. They are returning X and less than. Okay, so this is a tuple which they are returning, like this is, they are returning the value of X, and they are returning the result of this if condition. Okay. Just to show you, here we already.
What happens?
Yeah. So like if you just do symbolic trace of this toy example, it fails because it cannot do that. Now if you see here, the source code which was there, because of bytecode modification, they did the following. They changed the source code altogether. They did this. You have compiled function. There was this toy, the toy example was just basically this. This was the toy example. The toy example automatically got changed into this source code. Now what is it? It is calling compiled function 1 with A and B, getting the result temp2 and temp3. You guess temp2 was X, and temp3 is the conditional information. Yes, the condition. You store X in temp2, and then using that temp3 you do if, like that result becomes if, and then there are two continuations here. resume 30 at something, resume 30 and resume 38. Like these are some compiled generated name. So what is basically happening here is when you hit this either okay, when you hit this call or this, they name it as continuations. So when you hit this call, so basically the internal of this call is something like this. If you just look into, just try to print this, what is there inside this resume underscore this thing. So it is something like this. For the thing like where this is the continuation for the if true thing. So you are negating it and returning x into b. And this is the continuation for the false thing. Okay, if you see here, like there are two continuations are here. Now the way Dynamo behaves is the moment you hit this path, it shall reset itself and start, like it shall keep those previous compiled function with itself. Okay, and then what it shall do, it shall start compiling this function again, once again. Okay, so now if you see, if you just allow Dynamo to do capture of this resume at 30 thing, so basically it shall do something like this. So just compiles it. Okay, its name is compile function from compile function 7 or something like that. And then with that continuation, they rewrite the continuation source code and it becomes something like this. Getting the point?
What it does?
It is a yeah. So
It's
like
the loading, but what it achieves by doing that?
like it shall be helpful, like things shall, when you do operator fusion and all and everything, you bring down to the inductor level. So here I am just showing you how Dynamo works altogether. Okay, so this is involved.
By the way, we have 10 minutes.
Yeah, like this is involved. I shall be taking one more meeting because yeah, it's fine. It's fine.
And there is lot of good paper at ASCOS of interest to us in ASCOS 24. So you should actually read those. ASCOS
No,
24.
it's out, but I didn't find it.
I'm quite of
So basically, like once you are doing this, you are teaching like this. This is another level of compilation happening altogether. So you're just teaching those compiled stuffs, and you are getting something. You get the point, right?
To summarize, just GTing.
You are just jitting, and dynamically you are where fx graph you cannot, like fx graph couldn't have given you a single graph altogether. You are breaking it and dynamically creating some fx graph out of it, and then you are dynamically modifying the source code to just paste in that compiled thing altogether.
So rather than, so the benefit is even if it is not FX graph related, it is JITs. So it's just JITting all the time. The interpreter won't be happy in present time because it will be compared to C.
Yes. So the internal stuff like that compiled function itself altogether, some will be some say some Triton code, compiled Triton code in some sense. You won't be going through the overhead of calling Python stuff.
yeah, okay, I see. So basically this will then help in performance because you are not interpreting.
Yes, you are reducing the amount of it. A lot is what I think.
Yes, true.
Because you have lowered it.
At once.
Yeah. So basically to move on, there is something known as guards. I was discussing. So the caching and like this functions and all which we are doing, right? It might fail based on the like input propagation which we have done. So if the compiled function is no longer valid, it is checked by guards, and when one of the guards fail, it does recompilation altogether. Okay. So I'm not like I'm coming to it. As in they maintain something known as guards, and like this guard is indexed by the input which we are having, okay, for a particular input. Like so what it does is as in this is a pseudocode some kind of thing. There are some cache entries and there are some guards. Okay, like this guard and cache entries go hand.
Basically, if the cache has changed,
Like
you want to catch it.
cache has
Cache
like,
contents.
no, cache content won't be changing. Right? The
Input has
input has changed as
So
a
that
result.
would
As a result.
invalidate.
No, I mean,
The-
so
Basically, the goal is to actually cache queries.
the way what I was thinking, so let's say that so these are placeholders in some sense, like A and B, these are placeholders. They are getting called. So now you have a cache. So cache entry is a compiled in some sense. If you want to index into the compiled code, you need to ensure that your placeholders have the same values. The A and B that are getting. So think of it as
So you have to find it.
yeah. So think of it as virtual address first. If either one of them change, let's say, if one is same, other one change, you will not be able to find it. So at that point of time, we cannot call the compile code, we just recompile it.
Yes.
I think that's what.
Yes, that is what it is happening here.
So basically, this protect against the
Input
calling
change,
something which is not.
which is it shall, if you just fall through it shall do some invalid execution altogether. So this guard is protecting against that thing.
Guard is just comparison, you can ask, but I think guard is just comparing few values.
Yes.
Right argument.
Yes, like as in just to give a very basic example where like there was some case where guard was failing altogether was like internally there was some CPU tensor. Okay, in the middle I bypass, like I was not regarding the guard and pushing that tensor onto the GPU. Okay, now what was happening? The code was that previous code which was compiled assuming that tensor is a CPU tensor. Now on the Triton side what was happening is it was complaining कि it is an illegal pointer, like is it a CPU pointer? Huh?
The function.
There are many things like they have metadata like tensor's device, that is also a metadata.
But as
Okay.
long as the type signature is fine, you can reuse the cache, right?
In this, for graph, it has other problems, but for some guards, it will be fine.
Yeah, so
The placeholder, so virtual addresses have to be same when you are giving it. That's a problem in FSS. That's a problem in CUDA.
It's not more flexible in that.
It's captured at once.
So if you want to play around, then you have to change the virtual physical address.
yes, and that is possible.
That is possible.
That was the essence of the DMLA paper, right?
It is very possible, right?
But if the address is being passed on, you just operate on it, and when it's compared like in normal program, they are passing virtual address.
No, I'm not saying so. What I'm saying is with respect to CUDA graphs, not with
CUDA
respect to
graphs,
this.
yes.
CUDA graphs, really, right?
Okay.
So like he's saying that there can be many guards, but in this example, the guard was just checking A and B.
Yes, it's a very simple example, and the guard was simple.
The other case, you might just want to see if it's a device.
Yes, it shall be. It's a like I am running this on the CPU side. So just to give an example, where this, see, yeah, you can see utils device current device equals to null. None means CPU device. Each of the situation they have some guard. If it like, is not matching, they shall be recompiled.
You expect a GPU tensor, and if you receive a GPU tensor, you recompile it.
Yeah, so that is the point. Just to give, I shall be ending with this thing with the front end part. So basically, it is something happening like this. The picture says 1,000 words. So you had this red thing was there. It was compiled in your some function, and then there was this blue thing, which is the true case of like what is happening with this if condition. It got inserted in some like continuation, and again like this thing again got inserted in some continuation, and then there is this backend compiler and all, and it got stitched together in this toy example somehow, and this is protected by a guard function. Okay. So I am stopping here. Like
This is the output from TorchDynamo.
yes,
Now we will go to the backend.
yes, back next thing. Sorry.
So what? Recall it. So DBH lists down the results of breaking effects graph. under what
No,
function
no,
is
no,
it?
I didn't get
There is
that.
one side by side, if you want to see under what function CUDA graph fits, which we have
Yeah,
already on
we
list.
have that thing, कि like where CUDA graph flex. Like, yeah, I've had plans, but
No, 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 now finish your.
yeah, like I
But
was,
I don't think the wrong extension.
yes, because that guard failing thing, it is really a pain. I am just the last week's thing, right?
Yeah.
Yeah, I'm looking into it. Like changing those guards and all resetting is a pain in some sense because many things. So what I like, I was trying to follow your suggestion in some sense. कि like why not do something way before like these guard creations happen altogether? Okay, something at the Python start and Dynamo beginnings in that portion. I was trying to do it. I have got some pointers. Like I guess it would be doable.
Okay, sounds good.
You mentioned what are things you